All right, so in this example, let's pretend that you are an Olympic curling athlete training for the next Olympics. If you weren't aware, curling is a sport that relies entirely around changing the coefficient of friction. The mass of the curling stone is actually 19.1 kilograms. After you give the stone a push, calculate the force of kinetic friction between the stone and the ice, provided that the coefficient of kinetic friction is 0.1. So I'm going to solve this problem the exact same way I solve all of the problems in this unit. I will draw an interaction diagram and then a force diagram for the curling stone. I've gone ahead and drawn my interaction diagram showing both friction and the normal force acting between the ice and the stone. Notice I have not drawn the person in my interaction diagram because the person is no longer interacting with the stone, right? This is after they've pushed it. So make sure you do not include an interaction between the person and the stone. I've gone ahead and drawn my force diagram showing the normal force from the ice on the stone pointing up, the gravitational force on the stone, or the stone's weight force, pointing down, and the force of kinetic friction, in this case pointing to the left. I've assumed in my setup that the stone is traveling to the right, so I've shown the force of kinetic friction opposite the direction of motion of the stone. And again, I did not draw an applied force on the stone from the person because at this point the person is no longer in physical contact with the stone and can no longer be providing any kind of applied force. I'll write out my equations. In this case, I'll begin by writing out the equation for kinetic friction. I know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. And in this problem, I've been given the coefficient of kinetic friction. So all I need to do is solve for the normal force once again. To do that, I can actually just look at the y direction on the stone and look at the sum of forces in the y direction, similar to our previous problem. If I do, I'll see once again that if I call up positive and down negative, the sum of the forces would be the normal force minus the gravitational force. Since the block is not accelerating up and down, that would be equal to may, but a is 0. So then I know then that Fn is equal to Fg. Again, just in this scenario, it's not always true, okay? So if I know then that Fg, I'll also write that up here, Fg is also always equal to mg. This is our weight force, right? Then that would be the m of the stone, which in this case is 19.1 kilograms, and then g is always 9.8. So that means my normal force in this case is going to be equal to 187.18 newtons. So then my force of kinetic friction would be 0.1, that's the coefficient of kinetic friction, times 187.18, which will be equal to 18.7 newtons. All right. Now, when you're curling, right, not that I've ever curled, but you can sweep the ice, and you'll see athletes sweeping the ice vigorously. What they're doing is they're heating up the ice, and what that does is it melts the top layer and reduces the coefficient of friction drastically. And so let's calculate the force of kinetic friction after you sweep the ice, reducing the coefficient of kinetic friction to 0.04. My interaction and force diagrams will not change, so I will not be drawing those again. We'll just go ahead and use the same information from above. Also, please note the mass of the block did not change, the gravitational force did not change, and there are no other forces in the y direction. So the normal force is still 187.18 newtons. I don't think I've mentioned this yet, but this is actually a Greek letter. So this is mu sub k, if you're going to say this out loud. So the coefficient of friction, we use the Greek letter mu to represent that. So I can use the same expression before, where the force of kinetic friction is my mu sub k, or my coefficient of kinetic friction times the normal force, which would be equal to 0.04 times 187.18 newtons, which will give me a frictional force of essentially 7.5 newtons, which you can see is much less, obviously. All right, now let's take a look at how we can use this approach and also connect this to kinematics. All right, so continuing with the curling example, let's assume that you release the curling stone with an initial velocity of 6 meters per second, okay? We're going to calculate the acceleration of the curling stone both before and then after sweeping, or with and without, and then the horizontal displacement of the curling stone in both cases. And this might be important to know because the sheet of curling ice is actually about 45 meters from start to finish. And obviously curling, it's very important where the actual curling stone lands. That's pretty much the whole game. So let's take a look. To solve for the acceleration of the curling stone, I'm going to use Newton's second law and my sum of forces. Then I'll use that acceleration to solve for the kinematics. And the reason I know that is because I don't have enough information to solve for the acceleration from kinematics, so I'm going to use Newton's second law. So in this case, I'm talking about the horizontal acceleration, so I can say that the sum or the net force in the x direction would be equal to the mass of the stone times the acceleration of the stone in the x direction. But again, when I think about the sum of forces in the x direction, I only had that kinetic frictional force. And so I can say in this case, if we just, we can call left positive in this problem. So we're going to go ahead and I'll just draw my coordinates here. I only have the one force, so I'm just going to make it positive. So I'll say that the force of kinetic friction is equal to the mass of the stone times the acceleration in the x direction. So in this case, if I were to solve for A, I would rearrange this as such. I would divide both sides by the mass of the stone. And then that would give me that the acceleration in the x direction is the force of kinetic friction divided by the mass of the stone. And so looking at my answer from previously, that was 18.718 newtons. I rounded for my previous answer, but I'm using the full answer for this to avoid rounding error, divided by the mass of the stone, which was 19.1 kilograms, which is equal to 0.98 meters per second squared. And I'm going to say to the left, just to be very explicit about the direction of the acceleration. And if I were to then solve for the horizontal displacement of the curling stone, I would look at my kinematic equations. I'll go ahead and write them out for reference. And in this case, I'm looking for delta x. So I'm going to highlight that in all of my equations. Oh, I only have two. And then I'm going to ask myself, well, how about this first equation? Do I have time? I don't, no. So that one's probably not the one I want to use. Do I have everything in the second equation then? Do I have final velocity? Yes. I know that when it comes to a stop, that means that VF is going to be equal to 0. Do I have my initial velocity? I do. I was told that was 6 meters per second. And my acceleration I just calculated. So what I'm going to do is rearrange this equation to solve for delta x. Right, so if I take my equation, I immediately see here that I have some vi squared term being added here, so I'm going to subtract the vi squared from both sides. So that's vf squared minus vi squared is equal to 2a delta x, and then I want to get delta x by itself, so I'm going to divide by 2a. I always do my addition and my subtraction before I do my multiplication and my division. So then that tells me that my delta x will be equal to, right, the final velocity squared minus the initial velocity squared over 2 times the acceleration, which if I plug in my values, I would get 0 squared minus, in this case, I'm going to draw a little sketch here. If this is the curling stone, and the curling stone has a velocity, this is not a force, but there's a velocity to the right, then I know that the frictional force, right, this is a force, but again, this is not a force diagram, it's just a sketch. So if I'm calling this positive, right, then my velocity is going to be negative, right? Because it's going in again, they're opposite directions. So in this case, my acceleration, I'm calling positive to left. So I'm going to say this is minus a negative 6 squared. Since it's squared, it doesn't really matter, but it's important because later when we have problems, the velocity, may not always be positive. So please keep this in mind. 2 times 0.98. Again, we're going to start using acceleration as our positive direction, so I want you to be comfortable with this process. Okay, that would be 36 over 1.96, which would be equal to 18.4 meters. Okay, and as you can see, that is nowhere near close to the end of the curling rink, so that's why it's important to sweep the ice. Okay, so let's now take a look at the acceleration of the curling stone with sweeping. Nothing changes. My expression is the exact same. The acceleration is still the force of kinetic friction divided by the mass of the stone, right? None of our forces or interactions have changed, just how strong the frictional force has changed. That's actually going to be equal to that 187.18. This is my Fn, right? This is my Fn times the coefficient of kinetic friction, which in this case is now 0.04. That's that mu sub k. and that'll all be equal over 19.1 kilograms. Again, this is in newtons up here. And that will be equal to 0.392 meters per second squared. Again, making sure I'm not rounding at all here to make sure that I'm not getting any rounding error. All right, now then I would go ahead and I'm going to use the same exact expression. I did all the hard work already. I can just use that final expression. Again, nothing's changed here. I have all my same information. That will be the velocities at the beginning and end did not change. So I'm going to go ahead and express that the same. 2 times 0.392, and that will be equal to 45.9 meters. All right, much closer. So hopefully by the end of this example, you've seen how we can use Newton's second law and our force diagrams to solve for the acceleration of an object, right? And then we can use that acceleration later in kinematics to solve for things like displacement and other variables of interest. So this process will be the same for all of the problems in this unit. Okay, let's take a look at another example.